Okay, so this is the lecture that's going to replace the one that we missed this morning due to snow. So it's going to be a little bit different than normal because I'm going to have trouble with the video getting it to toggle back and forth. So I'm going to present a bunch of information here, and then I'm going to turn off the camera, set up again, and write out some of the problem solutions. And so you may want to toggle back and forth between videos, watch some examples, watch a new concept, watch some examples. Okay, so the first thing I want to start off with, which we will every class for a while, is this is a toolbox class. So we're adding tools already to our toolbox. What do we have so far? We have Ohm's law, V equals IR, KVL and KCL, which are just summations. Some of the currents out equals 0, or some of the voltage drops equals 0 around the mesh. We also now know how to combine resistances in series and in parallel. Today we're going to add dividers. That's a particularly easy way, quick way to solve some circuits. And then we're going to look at source transformation, which is really very important for both solving circuits and for when we talk about Thevenin equivalence next week. Okay, so let's first talk about dividers. We'll start with a voltage divider. And this is a case where you have something like this. You have a circuit in series, and then it's in series, and you want to know the voltage drop across each one of these resistors. Well, the first thing you could do is find the current through them. That's just going to be the voltage divided by the total current. The total resistance. But now that I know the current that's flowing, I can very easily find the voltage across the first resistor. It's just IR, so this one, here's I times R. And I can find the same for the second resistor, the same current, but now times the second resistor. And so you notice that there's a pattern, and we tend to write it this way. Voltage is voltage across whichever resistor it is the voltage across the two of them, the pair, or in this case it can be extended actually to theoretically an infinite number of resistors, times the resistance where you're interested in the voltage divided by the total resistance. And so again, we can have more than just two resistors. So this is very quick. So if we see that we just want to find the current across R2, that's easy. It's just R2 divided by the sum of the resistance times the voltage. So that's very easy. Current division is also easy. It has one little twist. So this is a case you might have like this. So you have current that's flowing, and then it divides. Hence the name. So how much current goes how much current goes through each resistor? Well, we could combine these. We know they're in parallel because the top of each resistor is the same node, and the bottom of each resistor is the same node. So we could find the equivalent resistance. And here, because I don't have numbers, this is where I'm going to use this form. And the reason I'm doing this is because if I could find the voltage here, then I'd know the voltage across the resistor, and I could find the current. So the voltage there is going to be, now that I have a single resistor here, it's just the current through that single resistor. So the voltage at that node A is just going to be IR. So I times the equivalent R. Okay, but so now if I want the current through R1, it's just V divided by R. So the current through I1 is the voltage, I keep saying that wrong, the current through R1 is the voltage divided by the resistance. So the voltage here divided by the resistance. Note that these cancel. And I can write the same thing for, let me write it down here, same thing for I2. The pattern will be the same. The R2s will cancel, and so we'll have the following. So again, just a very easy ratio. The thing that's really important to notice is that the current through the first resistor has R2 in the numerator, and the current through the second resistor has R1 in the numerator, so they're switched. And that makes sense because the amount of current through is sort of the reverse of their sizes. If this is the bigger one, then more current flows here. And conversely, if this is the smaller one, what am I trying to say? Less current flows here. So that's why that they're reversed. So when we write it over here, for voltage divider, the voltage across R1 has R1 in the numerator. The current through R1 has R2 in the numerator. The voltage divider can be extended to any number of resistors. The current divider requires only 2 branches. If you have more than 2 branches, you have to come down to, you have to combine to get down to 2 branches, one that you're interested in and one that represents everything else. Okay, so that is voltage dividers. I realize I'm speaking very fast, so I'm going to try and slow down. Okay, so the second thing we're going to cover for today is called source transformation. And this one's really very important. I'm going to draw 2 pictures, and then we'll talk about them and how they are the same. Okay, so these two are equivalent if, assuming the R is the same value, V equals IR. So if I start with this one, I just multiply I times R, and that's my voltage. If I start with this one, I just divide by R, and that's my current. So let's think about why these are in fact the same. These right here are called terminals. And so what we're saying is we have the opportunity to connect this to more circuit. So this is, you can think of this as like a voltage supply that you're going to connect to more circuit. So whatever it is. It could be big, it could be simple. And so the same thing over here. So at present, no current is flowing through these terminals from here and from here, because the circuit is not yet complete. I have not yet hooked it up to the rest of a circuit that I'd be interested in. Same thing over here. The current flowing anywhere in here is, there's no current because it is not connected up, so it's not a full loop. So, okay, so let's come to this one then. If no current is flowing, what is the voltage here? And I'm going to write that VOC. OC for V open circuit. It is not connected. What is the voltage there? Well, here we need to remember that voltage is a potential energy. So we don't usually say it, but we actually, the official name is voltage potential. So here, the voltage potential between this one and this one is, well, this much. No current flows here, so no voltage drop. So in this case, VOC, let's call this V source, is equal to V source. So again, these are terminals so that you're ready to hook up to the rest of the circuit, but you have not yet. That means no current flows in here because it's not a loop. So the voltage here is the voltage here because it's ready and waiting. It has the potential to be used. No drop here because no current. All right, so let's look at this side. What would be the voltage here? Well, no current is flowing here or here, but this current is flowing around here, no problem. No problem. So the voltage between those two terminals is the voltage across the resistor. And the voltage across the resistor is simply I, the current through it, times R. Let's again call this I sub S. So this is I sub S. So if V sub S and I sub, if this holds, V sub S equals I sub S times R, then this and this are the same. So this is really about the voltage at the terminals being the same. There's no current coming out at these terminals because nothing's hooked up yet. So that's the same also. So there are two ways that we're going to use this. One way is to simplify circuits, because it might be that if this worked in parallel, maybe the rest of the circuit's in parallel. That would be great, because then everything's in parallel and we know what to do. Or maybe this is hooked up to a circuit that has a lot of series connections. If this could be made into a series representation, then it's all series. Again, easier to work with. So we'll use it first one way for solving circuits. And then additionally, we're going to talk about Thevenin equivalence, where we can take a whole big messy circuit and distill it down to just this, or equivalently just this. And the advantage to that is that then, let's say I've got a complicated circuit and I just want to hook up different resistors to it. Well, if I hook up one resistor of a given value, I've got to solve the whole circuit. And if I hook up a different resistor, then I've got to solve the whole circuit again. If I could simplify it to this or to this, now resolving the circuit is very trivial. So it's a way to either simplify circuit solution or to simplify a whole circuit, distill it down to its simplified representation so that we can try different values for what we would call the load resistance. This would be called the load. Okay, so that's the second thing. So that's over here, source transformation. The last one we're going to look at is delta Y. And this is one that has messy formulas. I don't use it very often in this class. I want you to have seen it. We'll do some examples. I'll show you how you know when it's useful. Again, I don't tend to use it very much, but you need to know. So. Okay, so this is called Y delta transformation, or equivalently T pi. And so what the way this looks is that you could, if you have, I have to draw on the diagram, I'm sorry, I'm not very good at that. If you have this, here I wish I brought more colors, marker. This is a Y, looks like a Y. I can change it to a delta configuration where I just have put resistors in a delta, and so now it looks like a delta, an upside down delta. Additionally, it might look like this instead. This is a T. Clearly all I've done is I've just pulled this up to straight. So the T and the Y are the same. And now I'm going to make a pi out of that. And so that's going to look like this. So I'll get that right. Right. Where these are all hooked together. So again, and if you look at it, that's the same, right? We've got the resistor going across the top, and then these ones, I'm just taking this and sort of spread it out. So T is equal to Y, and pi, looks like a capital pi, is equal to an upside down delta. Okay, the equations for this are a little bit messy. So let me give them to you. So delta to Y. So if you start with a delta and you go to a Y, you're going to use these. R1 is equal to, let me go ahead and, hang on a minute, let me write out the equations and then label some things. Okay, so we're going to a Y. So we're starting with the delta and we're going to the Y. And so, tell you what, hang on a minute, let me just get the correct orientation for the letters. I need to match the book letters in order. Okay, so if this is R sub C here, R sub B, R sub A, so you start with a delta and you're moving to the Y. Here's Y. So what if you mix up the order of the numbers, right? Those things don't work the same way. So let's take a look at this. R1 is equal to the product of the resistors on either side from the delta divided by the sum. So this is just the product of the two adjacent resistors in the delta divided by the sum. So you can go around. R sub 2 is just the product of these divided by the sum. R sub 3, the product of these divided by the sum. So that's the pattern here. Now, if you're going to go, not really conserve space, if you're going to go the other way, so you're going to go y to delta. Y to delta looks like this. R sub A is equal to R1, R2 plus R2, R3 plus R3, R1 all over R1. So clearly the numerator here is not going to change. Let's look at where RA and R1 are. RA is here. R1 is the resistor that's sort of opposite, in the opposite apex. So the pattern here is sum of product pairs divided by the resistance, I'm just going to say opposite. So again, a little bit messy, but it is handy for solving circuits to make them simple, because sometimes we'll run into a case where something, let's look at the difference here. This could then be parallel to something here where these two were not. And let me just do it, we'll do an example circuit, and I think that will make more sense. One last thing I want to point out is that if the R's are all the same, so if you start with a delta and all the R's are the same, then this is going to end up being R squared over 3R, 1/3 R. So if you start with a balanced delta configuration, when you go to a Y, it's just going to be 1/3. Likewise over here, if they were all the same, it would be 3R squared over R, 3R. The take-home point is in the Y configuration, the resistors are bigger than they are in the delta configuration. So if they're equal, it's a factor of 3. Okay, so based on that then, I think that's all the information I need to give you for now. I'm going to hold on Wheatstone Bridge. Maybe we'll cover that in lab. And again, diodes, there's some things I would love to cover, and hopefully we'll have time in lab sometime. But this is what I wanted to cover for today. So delta Y doesn't make this list just because the equations are really long, but every once in a while we'll pull it out and use it. But so far now we've got a pretty big toolbox. So let's do some examples using dividers and source transformation and delta Y conversions.